think back to the start of term 3 when we began this course. What is the theme of this course? What's the theme? Think deeply about simple things. Very good. Okay. So here's what we're going to do. We're going to take this situation, which seems kind of, well, innocuous and uninteresting, and we're going to try and dig into it. Okay. So, what have we determined so far? For the bridges of Königsberg, the problem is to try and cross all the bridges just once, right? That's the issue, okay? So this problem was actually presented to that most famous mathematician, Leonhard Euler. So this was like 300 years ago, okay? And Euler, he kind of has this way of getting into everywhere in maths. Like he contributed to all the different kinds of fields of maths that we know. And he was called the master of us all, okay? Now, what Euler thought about was that, well look, this problem here, it's very, very concrete. It's an actual city and there are actual bridges. But to consider this mathematically, you can boil it down, right? You don't need all of this, everything in this picture, okay? So for example, if I simplify this a little bit, and I'd like you to join me in doing this, okay? Like think about the shape of this river, okay? The shape of the river doesn't really matter, okay? This should be ringing some bells from something that we looked at under the topic beauty and mathematics. Do you remember we had a look at something else where the shape of it didn't really matter? Anyone remember? Yeah. Very good. Is when we're having a look at maps, and we're having a look at coloring maps, and in topology, which is related to this, the actual shapes of things didn't matter. It was their relationships, okay? So I'm going to redraw this, and I'd like you to join me. I'm going to redraw it in a simpler way, okay? So I'm going to draw it a bit like this. Here's my picture, like so. I've got one in the middle, one here. Okay, so when you have a look at this situation, right, there isn't much symmetry to it, is there? Right, like you got pairs of bridges and all that, but it's kind of lopsided. But actually when you think about the relationships of the land masses and the bridges, it is symmetrical. Let me get my, my bridge color here. Have a look. You've got 2 down and 2 up. Right? 2 here and 2 here. Right? That's symmetrical. You've got 1 across here, and then you've got again the 1 up, 1 down situation. Okay? So this is kind of a simplified version of this map, which helps you see the structures that are there, and you don't get distracted by the fact that this is bend in the river and all that kind of thing. But even this can be boiled down. Okay? Because for instance, see how you've got like a landmass here and a landmass over here. Right? Or a big landmass over here. The sizes of these landmasses in relation to each other, it doesn't matter, does it? What matters is what's connected, okay? So in fact, I'm going to say this is equal to something even simpler, okay? Instead of landmasses, if I just represent those as points, how many points are there, not bridges, how many points are there that are joined by bridges? Have a think. If you labeled them, what would they be called?
16.
So let's have a think about this. This here, right? This is a landmass. I see it has 5 bridges coming off it, but it's just one landmass, right? So for example, if I call that A, okay, what would be another landmass that I could name?
B.
What would you like me to call B? The one in the middle here? Yeah. Okay. So what should I name next? What would you like me to call C? Okay, the top. And you can see, by the way, that all of this, it's all one landmass, right? And this is D down here. So there are really only 4 places that I need to connect. Does that make sense? Yeah? We're going to simplify it even further. If all we have is these 4 things, these 4 places, okay, I'm just going to represent them by points, right? So if I have A here, you put B over here, we had C above and D below. So when I join these, all you need to think about is how many bridges connect all the points. So for instance, how many bridges are there between A and C? 2, very good. 1, 2. So far so good. How many bridges from A to D? Also 2. Right. And then you've got 3 bridges all coming away from B. Does that make sense? 1, 2, 3. Okay. So this is our kind of like mathematical abstraction of this. Does that make sense? So these are really all the same. Okay. Now when you see this, we should put some labels on these things. This is called a network diagram. In fact, this the bridges of Königsberg is a problem under the topic of network theory. Okay? Network theory. Which means something very important. You see this problem, you're kind of like, what's the point? You can cross it or you can't cross it. Who cares? Just go halfway across one bridge and come halfway the other. Or swim, or I don't know, okay? Well, when you realize this is about networks, okay? These kinds of problems are like kind of like the backbone of how things like the internet work, right? These kinds of problems are enormously relevant to engineers who are trying to make networks actually function, okay? So, we've got here 4 points. We call these vertices, right? So I would call this one like vertex C, okay? Vertex A, vertex B, vertex D, and so on, okay? Instead of bridges, what we call these things are edges. Okay, so you have vertices and you have edges, right? Now there are 2 ways to go through our city, our network, okay? The first way is with what we call a simple path. A simple path is just a way to visit every vertex and visit it once, okay? So usually a simple path is quite easy to work out. For example, I could go, I could start at C, I could go C to A to D to B. It's a simple path, I visited every vertex. Does that make sense? But what we're looking at is more interesting, right? Because this idea was pioneered by Euler, instead of being called a simple path, these are called Euler paths. Okay? So an Euler path is, can you cross every bridge once? Which is another way of saying, instead of visiting every vertex, I want to visit every edge, just once. Okay, so what we were looking for before is an Euler path through this diagram, through this network, okay? And the point is it doesn't exist and it can't